Okay, welcome to 7.3 Part 2 AP Calculus. Let's get a little zoom on here. And this is just basically our differentiation or our anti-differentiation by part, or our u-dv substitution. And we talked about our tabular method before. If you haven't seen Part 1, I'd recommend you see it. It helps set this one up. Excuse me. Okay, so I need to choose a u. I need to choose a dv. So my choice could be u is x cubed, dv would be ln x dx, or u could be ln x, and dv could be x cubed dx. And my first thought is, well, we've talked about the benefit of having polynomials be our u value, because now I could take x to the third, I could derivate that to 0, and I could use our tab method. However, I would have to be able to integrate ln x. And integrating ln x is no bargain. We don't know how to do it at this time, so that leaves me with no choice but to have u be ln x. And while we kind of pine about the fact that we wanted this to be u, you're going to see this works out pretty well. Therefore, dv has to be x cubed dx, so everything here is accounted for. I always set them up this way. We've talked about that in video 1. Now I need to find du, because I got to know du along the way. I mean, what do I need to know? I need to know u. Got it. Need to know v. Don't have it yet. Need to know v again. Wow, I really need to know v. And I need to know du. So du is the derivative of ln x, 1 on x dx. This is the derivative of v. I need the antiderivative of this. So v is the integral, x to the third, that is x to the fourth, on 4. We put these two together first, and we get the integral u dv equals u times v, this times that. So I've got x to the fourth on 4 ln x minus the integral of v, x to the fourth on fourth du times 1 on x dx. And we may be able to see right now, so this is our second part right here. You may see right now, hey, this might even be better than using our tabular method. So x to the fourth on 4 ln x just waits around for the integral of this. Little algebra simplification, the x to the fourth on x reduces. I'm going to pull the 1/4 out front. 1/4. That would be x to the third dx. So I end up with x to the fourth on 4 ln x minus 1/4. The integral of x cubed, again, is x to the fourth on 4 plus constant coefficient, and x to the fourth on 4 ln x minus 1 on 16, or x to the fourth on 16 if you prefer, plus c. Okay, very good. Now, b, once again, I've got a polynomial, and I can derivate that down to 0 real efficiently, real quickly. Can I find the integral of e to the x? I could find the integral of e to the x all day. That one's not going to be a problem. So I'm going to set this up in a tabular method, which basically says for u we are choosing x squared minus 5x. And it says for our dv we are really choosing e to the x dx. I'm just not going to write down the dx. It's not necessary for us. So for tabular method, we start with those. We derivate this down to 0. First derivative 2x minus 5, second derivative 2, third derivative 0. And that tells us how many times we have to integrate e to the x. This does not get any better, because e to the x, of course, derivative is e to the x, integral e to the x is e to the x. And then we take this product right here, the positive version of that, and add it to the negative version of this, and add that to the positive version of this, for a final answer. Maybe we'll simplify some things. X squared minus 5x times e to the x plus 2x minus 5 times e to the x. Oops, that's minus. You saw it before I did. That's minus. And plus 2 e to the x plus c. Now, pretty tempting here to see if we'd simplify. I mean, I can see if I would distribute this, I'd get some common x e to the x term, so maybe I will factor out the e to the x. And we get here, technical glitch, sorry, I get e to the x times, this would be x squared minus 5x. If I factor an e to the x out and distribute this negative, I get minus 2x plus 5. If I factor an e to the x out, I get a plus 2. I can't factor an e to the x out, plus c. So what do we end up with? I'm going to put my x's first. Just an x squared minus 7x's plus 7 e to the x plus c. I like that answer. Okay, so anytime we see these, truthfully, here's kind of what should be going on in our mind. If we just see this and it wasn't in 7.3, I should say, integration, I've got a function of y times a function of y. Can I do this with u du? Well, if I choose e to the y to be u, the derivative of that is e to the y, and that doesn't help out with sine. If I choose sine to be u, then du would be cosine, and that doesn't help out with e to the y. So my next choice then is differentiation by parts, or u dv substitution. Well, first thing I look for, polynomial. Why? Because if I got a polynomial, I can derivate that down to 0. I don't. E to the y will not derivate to 0, and if I integrate e to the y, yeah, that works. Integration works, but sine of y, if I choose it to be u, it will not derivate down to 0. So, I don't know which way I'm going to go. I guess I'm going to choose and be willing to erase, if it causes problems, u is e to the y. Then I'm going to have dv, which I'm always going to set up next to u. dv has to be the rest, so that's sine of y dy. If there's a d on the left, there's a d on the right. So du, the derivative of e to the y, is e to the y dy. And the integral of sine, or v, wants to be cosine, but is the derivative of cosine sine? No, the derivative of cosine is negative sine, so I have to do some accounting here. Okay, well, so far so good. Let's see how we do. I've got u times v, so I've got a negative e to the y cosine y minus integral of v du, that is negative, I'm going to put the e to the y next, cosine y dy. And I think I see where we're going with this. This is one of those problems that kind of is one of those little challenge problems where we just keep going and hope something good happens for us. You'll see what I'm talking about there. Quick cleanup of this. Negative e to the y cosine y plus integral minus minus plus e to the y cosine y dy. Now at this point, I might be tempted to go back and change u, change dv, flip these around and give that a try, but I'm going to promise you you're going to end up in a similar situation there. So what do we do now? Now I have to try to integrate this, and I have to ask this term just to be patient for a while. So here we go. I'm going to stick with my pattern. U is e to the y, dv is cosine y dy, du again is e to the y, in this case dy, same as the last case I guess, and v, the antiderivative of cosine wants to be sine. Is the derivative of sine plain old cosine? Yes, so we're good. So I ask this guy to be patient up here. I'm going to have to write a little bit small next to this, kind of boxing myself in. This negative e to the y cosine of y has to wait around for the integral of this product e, oh, hang on. Now I really got to write small. The negative e to the y cosine of y plus has to wait around for the integral of this. Now that breaks up into this times this, so I'm just going to put a big bracket here. That is e to the y sine of y minus the integral of those e to the y sine of y dy. And here's where we're hoping maybe something good has happened for us. All right, quick simplification here. Just getting rid of some parentheses here. Right now, I'm solving for this function. I've got integral e to the y sine y dy equals negative e to the y cosine y plus e to the y sine y, and then minus my integral right here, which is this guy. Sorry about that. Ran out of some room there. But what do we notice about this guy? This guy is exactly what we started with. These are a match. So it's like I've got an apple here and a minus apple there. And what do I not like about this side? I don't want the integral there. So I'm going to add an apple to both sides. And I get 2 integral e to the y sine of y dy is negative e to the y cosine of y plus e to the y sine of y, for a final answer of, divide 2, and I've solved for that. Negative e to the y cosine y plus e to the y sine of y on 2. What could we do to this? Maybe to clean it up, and I don't even know if there could be an argument made that this is more simplified, but I think the back of the book on this would have this something like, let's take out a negative e to the y, or just an e to the y. I'm going to take out negative e to the y on 2. And what does that leave me with? Cosine of y minus sine of y. Or it could be e to the y on 2, sine of y minus cosine y. Just a little bit of algebra manipulation. So that's kind of a filthy problem, and that's what we're going to look for when we get something that is just continuously integratable and continuously differentiable. We're going to look for maybe we just don't have a way to get out of that, so we're going to try to go until we get a match. It could actually be worse than this, but pretty cool problem. You've got 1 or 2 like that in your assignment, and here is your assignment from that. And don't hesitate to come in and ask some questions if I can help. Good luck.